Algebraic patterns and introduction. Linear. Each polynomial function creates a pattern which can be studied both numerically and graphically. Patterns such as 0, 3, 6, 9, ... can be described by the function f of x equals y equals 3x, where x is greater or equal to 0 and x is an element of the natural number set. So drawing this out graphically, it's the red line. Okay, so we can see it's a straight line and it has a positive slope. So taking our x values to start at 0, so we're told that x is greater or equal to 0, where x is an element of the natural number set. Now 0 is not actually a natural number, but we do always start with 0 when we are using our x values. So we have x is 0, 1, 2, or 3. Our function is 3x, so we're placing the x with brackets and inputting 0, 1, 2, 3. Then our f of x, or our y value, or our output, is going to be 0, 3, 6, and 9. So they are the values that were given in the pattern, 0, 3, 6, and 9. So as couples, we get 0, 0, which I've plotted there at the origin. So I'm only plotting a few points, but we can see that the line does go on forever in both directions. So we get 1, 3. So there's 1, 3 on our graph. Then 2, 6, 2, 6 on our graph, and 3, 9. So 3, 9 on our graph. So the red line represents the pattern 0, 3, 6, 9. Let's take another pattern, 1, 4, 7, 10. So this can be written as f of x equals y, which is equal to 3x plus 1, where x is greater or equal to 0. So our x values, 0, 1, 2, and 3. Subbing into our function, we replace the x with brackets and we input 0, 1, 2, 3. And our output is 1, 4, 7, and 10. So that's what we started with. That's our pattern. So as a couple, 0, 1 is our first point on our graph. So that's that point there. So now we have a new red line. So this is representing the function y equals 3x plus 1. So then we have 1, 4. So that's that point there. Then 2, 7. That's that point there. And 3, 10. That's that point there. Now if we take another pattern, 2, minus 2, minus 6, minus 10. So f of x, our function, is equal to y, which is equal to 2 minus 4x, where x is greater or equal to 0. So our x values, 0, 1, 2, and 3. Our function, replacing the x in our function for brackets and inputting 0, 1, 2, and 3. And then our outputs, 2, minus 6, minus 10. So that's the pattern we were given. And then we form our couples and we plot them on our graph. So we get 0, 2, 1, minus 2, 2, minus 6, and then we don't have space, but 3, minus 10 would obviously be down here. And the line goes on forever in both directions. So this red dotted line represents the pattern 2, minus 6, minus 10. Each of these number patterns has a constant amount added or subtracted between terms, and each, when graphed, produces a straight line as shown. Functions of the form f of x equals y equals mx plus c are called linear functions. So you should recognize this from coordinate geometry. So y equals mx plus c is the equation for a straight line, where m is the slope of the line, and the c is the y-intercept. It's where the line crosses the y-axis. In a linear pattern, the difference between consecutive terms, called the first difference, gives m the slope of the line. So if our pattern is 0, 3, 6, 9, 12, ... The first difference, to get from 0 to 3, we add 3. To get from 3 to 6, we add 3. To get from 6 to 9, we add 3, and so on. So the first difference is 3. So if we have our equation of a straight line, y equals mx plus c, the m is going to be 3, because that's the first difference. So it's going to be mx. And the plus c is going to be 0. So that's the starting point of our pattern, which is 0. So we don't bother saying 3x plus 0, we just say 3x. And the 0 is also going to be the y-intercept. So this line, if we draw this out graphically, if we draw this pattern in graphically, the line will cross at the origin, 0, 0. So the starting point of each pattern determines C, the constant term. We note that when x is equal to 0, geometrically, we get the y-axis intercept C, i.e. the line goes through the origin, 0, 0. So we have y equals mx plus c. This is the equation of a straight line. We replace the m with 3 because that was the common difference. We replace the c with 0 because that was the first term in our pattern. And it simplifies to y equals 3x. We just get rid of the 0. So that's why we call this pattern f of x equals y equals 3x. In terms of the nth term formula, Tn is equal to a plus n minus 1 times d. So the 0 is going to be a, because that's the first term. The d is 3, and that simplifies to 3n minus 3. And just to note that the minus 3 is our 0 term. So if you were to go back by 3, you'd end up at minus 3. So you always end up with your 0 term in your nth term sequence formula. Taking the second pattern that we looked at, so the second pattern was 1, 4, 7, 10, 13, ... Again, the first difference is 3. So again, we have y equals mx plus c. We replace the m with 3 because 3 is the first difference. And we replace the c with plus 1 because 1 is the first term of our sequence. And it also happens to be the y-intercept. If we were to use our Tn formula, we would have Tn equals a plus n minus 1 times d, replacing the a with 1 and the d with 3. And we would end up with Tn equals 3n minus 2. So notice now that the formula, the equation of the line, the function is different to Tn. So the equation of the line is like the name of the line, whereas Tn is the little formula that you use to generate terms. So if you wanted the 10th term, you would sub in 10 in place of n to figure out what the 10th term of the pattern is. It's very important to notice that you get two different things. So you have minus 2 in your Tn formula, and you have plus 1 in your equation. So the equation of the line is like the name of the line, whereas Tn is what you use to generate terms of the sequence. And just note that if you were to subtract 3, so if you start at 1, which is the first term in your pattern, and you go back by 3, you end up at minus 2. So that's technically term 0. And minus 2 is in your nth term formula. So you'll always have the 0 term. It's actually just a really quick way of working out Tn, but you can obviously use the formula if you're more comfortable with that. Then our third pattern was 2, minus 6, minus 10, minus 14. The difference between each term is minus 4. So our function is going to be f of x equals y, which is equal to 2 minus 4x. I don't know why the book decided to put the 2 in front. Normally, the term that contained the x value would come first, but it doesn't really make any difference. So 2 in this case is your first term of your pattern, and the minus 4 stuck onto the x. So the minus 4 is going to be your m. So the slope of the line. So minus 4 is the difference, so that gets stuck onto x. So our equation of a straight line is y equals mx plus c. We replace the m with minus 4, and we replace the c with 2. So 2 is your y-intercept. So remember, this is the name of your line. This is the equation of the line, or the name of your function. But if you wanted to come up with the nth term, which is obviously different, you can use your nth term formula, replacing the a with 2 and the d with minus 4, and you end up with Tn equals minus 4n plus 6. So the Tn formula, you can use it to generate any term in your sequence. So if you want the 100th term in the sequence, you swap the n for a set of brackets and put 100 into the brackets, and you calculate the 100th term. So it's important again to note that Tn is different to the equation of the line. The equation of the line is like the name of your line, or the function. It's different to Tn, but they're very, very similar. And just again to note that if you start at 2, if that's your starting point, and you go back by 4. So if we're subtracting 4 each time to get the next term, you're going to add 4 to get the previous term, to get term 0. So term 0 is 6. So that's why we end up with a 6 here. So again, it's a quick way to get the nth term if you want to use it. But you can, again, just use the nth term formula from your formula book if you're more comfortable with that. So very important to note that functions and patterns are very, very similar, and that you can generate the function of a sequence, which is the equation of a sequence or the name of the sequence, but it's different to Tn. They're similar, but they are different, and it's important to note the difference. So the plus c at the end of your equation will always be the place where the line will cut the x-axis, and the coefficient in front of the x, so the number stuck onto the x, will always represent the slope of your line. So this is where coordinate geometry links with sequences.